morning and welcome. My name is Tabata and I am a member of the marketing team at Bmax. Thank you for your attendance today to our very first webinar dedicated to the simulation process. Gilles Mazars, the head of simulation at Bmax, will present a few case studies to demonstrate our approach and expertise. If you have any questions during the session, you can submit it directly on the private chat box located at the right and the bottom of your screen. If you are on a mobile version, you can find this chat box in the middle and the bottom of your screen. Gilles will provide answer at the end of the presentation, and if you don't have time to answer to every question, you will receive a personal answer by email very soon. I'm going to turn it over Gilles now, and I wish you all a very good webinar.
Tabata. Hello, I'm Gilles Mazars. Welcome to this Bmax webinar about simulation. Your first question could be, why simulation? There are two main reasons. The first one is simulation can be didactic. It can be easier to explain physics and to understand HPP processes thanks to simulation. The second reason is we want to promote our simulation service. After more than 10 years of experience to solve complex problems, we want to propose our experience, our skill, our resources to a response to your needs in terms of finite element analysis, for static solution or fast dynamic, for simple approach or multi-physics approach. The best way to show you what we are able to do is to describe all the Bmax activity in terms of simulation. After a few words about Bmax and simulation software and objectives, we'll describe HPP principles and the special simulation capabilities to activate to address this kind of problem. After we detailed all simulation activity in Bmax, and we will we highlight how we can the benefits of simulation for each process with very simple study cases. And at the end, we describe the simulation service. Bmax has developed innovative process and provides with equipment and service using high pulse power, HPP, for industrial applications. Basically, the product of Bmax, it's a pulse power generator. It can be plugged on several devices to generate dynamic mechanical loading for manufacturing applications like forming, welding, assembling, and calibrating. For forming application, for example, we develop a specific system to form unipolar plate. It's a main component of the fuel cell stack for application of electrical vehicle powered by hydrogen. We have a team regarding complex part forming dedicated to forming processes for aeronautic, automotive, and luxury applications. And a last example, in welding, we have a team dedicated to assembling a pressure vessel, HVAC, CO2 accumulator for automotive equipment. When we deploy generator in a plant, you can enjoy a lot of services, engineering services, and like electrotechnics, automation. For example, it's like a plug-and-play system. We plug the system, you can play with it, and you can enjoy any trainings to know how to play with it. In this webinar is focused on simulation service. Here it's a presentation of the HPP process. In blue, it's the generator, including control cabinet, capacitor bank, and a trigger, a switch. We can plug the final stage of the system. We plug a coil for magnetic pulse welding, for example. In this case, it's a 1-ton coil for cylindrical shape with a flyer and a parent part. So thanks to the control cabinet, we fix the energy level, the voltage. We load the capacitor bank. We store electrical energy. And we close the switch, and we release this electrical energy into the coil. The coil is a specific device. When we apply a non-constant current inside, it creates magnetic field, the blue line in this case. And if you put a metallic part in this magnetic field, it creates induced current. And the combination between magnetic field and induced current creates the Lorentz force. And thanks to this driving force, we are able to weld to crimp. We can plug the generator on another geometric coil for magnetic pulse forming. Here it's a flat coil, multi-turn coil. We put a flat blank. And if we change the geometry of the coil, we change the loading. We change the magnetic field. It's like a sculpture of the loading. And we induce the current, and the combination between magnetic field and induced current push the blank into in the bottom of the die. It's magnetic pulse forming process. The last kind of process, it's electro-hydraulic forming process. In this case, we plug the generator on the electrode system with a die, and between the electrode system and the die, we put a flat blank. In the water, we release all electrical energy from the generator, and we create pressure wave. Electro-hydraulic forming process, EHF, consists to use this pressure wave to form the part. It's an overview of all the HPP process in Bmax: magnetic pulse forming, magnetic pulse assembling, and electro-hydraulic forming process. In terms of simulation, we define 4 main objectives. Understand physics. As you understand, HPP process are multi-physics and dynamics, and we don't have very accurate rules, analytical or mathematical formula to design the process. That's why we use simulation, finite element software. Build predictive model. The first step consists to refit experimental results and to extrapolate them to build templates and methods. By this way, we save the accuracy of simulation, and we can be predictive. Answer faster to the customer demand. We can save cost and time thanks to simulation compared with building of a brand new prototype or upgrading of an existing setup. So simulation can be less expensive, and the time scale can be reduced due to the simulation. And the last objective, it's a customer requirement for large customers. When we speak about complex process or innovative process, we have to give the proof of our ability to do the job and to validate feasibility, for example, by simulation. We use LS-DYNA software. It's a finite element software, multi-physics. We can perform any coupling between mechanical solver, fast dynamic, and other solvers like electromagnetism, fluid solver, ALE solver, and heat transfer. The uniqueness of Bmax has been developed since more than 10 years with numerical method, of course, but not only. We developed specific measurements to catch the variation of value during the test with optical sensor, and we try by simulation to refit all these variation of value during the process. The process is a very, very short time scale. And if we have a good compliance between this measurement and the experimental result and numerical ones, we can have a good level of confidence in our simulation. We have a PhD who developed electro-hydraulic model to make the link between electrical property of the generator and the pressure wave generated in water for EHF applications. We have 2 PhD who worked on material characterization. We developed specific test bed to characterize the material and to define the behavior of material in function of strain rate in dynamic. It's very important to have a very accurate definition of the material behavior in good description in the software to save the accuracy of the simulations. Regarding LS-DYNA, we are beta tester since 2005. We are the most important user of LS-DYNA and electromagnetic module in France. And we developed specific capabilities like welding windows, user loading, user equation of state, or material law. And we can develop any data processing in function of need. Few words regarding HPP principles. HPP, it's high pulse power. So what is the power? The power, it's a variation of energy in function of time. Significant variation of energy in a short time, it's a high power. If we consider a catapult, We store mechanical energy very slowly, low power, and we release all this energy in a very short time. It's a mechanical high power system. For Bmax application, it's quite the same, but with electrical energy. We store electrical energy slowly. It's low power, and we release it in a very short time. And the signal is damped. That's why we speak about high pulse power. All the key point is this process, the high pulse power are fast dynamic. All is done in few microseconds. The second point is for all Bmax application consists to convert electrical energy in mechanical one. Left on the side, it's magnetic pulse processes, welding, crimping, and forming, where we plug the generator on a coil. It's a specific electrical device. When the current is applied on this coil, it creates magnetic field. And a metallic part, if we put the metallic part in this magnetic field, we create induced current, and the combination between magnetic field and the induced current creates the Lorentz force. The Lorentz force, it's a mechanical energy. All magnetic pulse application consists to create Lorentz force. And by this way, we're able to convert electrical energy in mechanical energy. The second kind of processes are electro-hydraulic forming processes. We plug the generator on an electrode system, and we put this electrode system in water. When we release electrical energy from the generator, we create a lightning between these two electrodes in water. It's a plasma explosion, and this plasma pushes the water surrounding the channel and create a pressure wave. The pressure wave is the mechanical energy. So fast dynamic and multiphysics. In simulation, we have to activate specific capabilities to be fast dynamic and multiphysics. For magnetic pulse application, welding, crimping, or forming, we perform a coupling between the mechanical solver, fast dynamic, and the electromagnetic module. As you understand, the loading, the magnetic field, depend on time, pulse power, and it depends on the distance between the conductor parts. So the mechanical solver sends to the electromagnetic module the distance between the conductor at each time step. The electromagnetic module updates electric field, magnetic field, current density, and at the end, the Lorentz force. And it sends this force to the mechanical solver. In the nature, when we apply the current inside material, we create heating, temperature increase. That's why we perform a coupling between the thermal solver and the electromagnetic module to update the temperature, and by this way, update the conductivity of the material. And when the temperature increases, the conductivity decreases, and the Lorentz force at the end decreases. So to be accurate in the calculation of the loading, we have to activate this coupling between thermal solver and electromagnetic module. For active components like coil or field shaper, the gradient of temperature is significant in the skim depth, and we have to calculate the thermal expansion to be accurate in the estimation of stress component in this active zone. That's why we perform a coupling between thermal solver and mechanical one. In this example, we consider a multi-turn coil, flat coil. We apply directly a pulse current on the red part, and it's a magnetic pulse forming process. We consider a flat blank, and we want to push it in a deep die with a face in the bottom. The fringe, the colors, represent the maximum of Lorentz force. As you can see, it's not constant in time, it's not uniform in space. The maximum of Lorentz force are like a shadow, an imprint of the shape of the coil to the blank. And it's the result of the coupling between electromagnetic solver and the mechanical solver. As you can see in the center, we have a blue spot. There is no Lorentz force, and it's not possible to calculate such loading without these capabilities of coupling between this solver. In this case, all the process is done in 64 microseconds. For electro-hydraulic forming process, we perform a coupling, full coupling between the structure, the mechanical solver, fast dynamic, and the fluid solver, ALE solver, fast dynamic too, with arbitrary Lagrangian and Eulerian solver. It's for Eulerian approach, a fluid approach. Thanks to this solver, we calculate the wave propagation into the liquid. water in this case. And when we calculate the wave propagation, we can directly apply this pressure wave on a deformable blank thanks to a fluid structure interaction. It's like a numerical contact. In this example, the wire in red defines the water volume. We consider 2 electrodes. In blue, it's a blank, deformable part, and we want to push this blank in the green part. It's a rigid die. So we perform an energy deposition between the electrodes, and all the fringe represent the propagation of pressure waves. As you can see, the incident wave creates an initial velocity on the blank. We have a first reflection from the sidewall, and we complete the forming with a combination of the top reflection and the second reflection from the sidewall. So it's one discharge and a three steps forming. Without simulation, it's not possible to imagine a such forming process. All the process is done in 280 microseconds. In terms of simulation activity internally in Bmax, we can quote principle, expertise, training, and development. Regarding principle, we work before a project, operational project or research project. We can perform any principle study, feasibility, or we can provide with technical data for quotation to choose a generator, for example, for specific applications. We have expertise on simulation, of course, in HPP processes and in conventional forming process. We can perform any trainings internally regarding engineering tools or HPP process, and we develop these tools and in Python or Excel. Regarding operational project, basically, a customer can give us a sample of the material and the CAD file of the expected part. And we deliver a system, or we can produce part. We can use simulation to perform the material characterization. We cut a specimen in the sample to define the behavior of materials, and we can use this data in our software to perform design and optimization of component of process. During the test campaign or prototype phase, we can use simulation for technical support and to optimize the settings, to reproduce a defect, to investigate, and to fix it. So to describe all these kind of activities, we highlight the benefits of simulation for each process with a very, very simple study case. The first one is calibrating. Here we want to form, with a conventional forming process, a plate with 2 grooves. It's a steel 1 millimeter thick. We use a punch, and we form these 2 grooves with a punch and a die. The topic of simulation, at the end, when we remove the punch, we create a defect of springback. It's a twist defect. So we want to use simulation to reproduce this defect, to understand the origin of this defect, and to imagine a solution to fix it. So first of all, we reproduce a conventional forming process. We form 2 grooves into the plate, and we reproduce the defect. We analyze the stress distribution before and after the springback to understand the origin of this defect. After, we imagine a discharge chamber, an electrohydraulic forming process to restrict the plate at the center and to change by impact the stress distribution. And by this way, we're able to fix the defect, the twist. And the color represents the displacement normal to the plate before calibrating and after calibrating. It's an academic example. Regarding EHF, electrohydraulic forming process, here we use simulation to perform material characterization and to design. The product is a memory stick. It's a Bmax goodies. It's a luxury product. We want to study 2 materials, 5657 and 1050, 0.8 millimeter thick. So we try to design all the EHF process with simulation. First of all, we characterize material, both material, in static, in dynamics, and we try to catch when the critical thinning, the necking occurs, to fix the elongational break. It was defined at 1050 at 41%, and for the aluminium 5657, 35%. After, we perform 2D simulation to optimize the preformed geometry. It's a tube with a bottom, and we want to optimize the radius in the bottom, 1 millimeter, 2 millimeter, or 5 millimeter. With 2D simulation, we're able to say the optimized preformed geometry, it's with a radius of 2 millimeter. In this case, we reduce the thinning, the strain, and we are able to form without crack. After, we perform 3D simulations to check if we respect all the requirements and to identify where are the most critical area in terms of thinning. According to the 3D simulation, the most critical area is in the bottom with a thinning of 38%. During the test campaign, if we use, so the conclusion of simulation consists to say the optimum settings are to use 1050 aluminum annealed with a preformed geometry of 2 millimeter in the radius. In this case, we're able to form this part. During the test campaign, when we use the other aluminum, 56, 57, crack occurs exactly in the area defined by simulation. And the only one way to form this part is in the respect of the condition of the settings defined by simulation. The next example, it's again electro-hydroforming process. But in this case, we use simulation in technical support and after to optimize the process. The part, it's an oil deflector in aluminum 6061, 400 millimeter in diameter, 1 millimeter thick. So we want to use simulation to design a new EHF process more efficient. The first step consists to reproduce the experimental result from the previous test campaign, where we used large water tank for versatile water tank to form large panel for aeronautic applications. In simulation, we reduce the water tank and we reduce the energy level as a number of discharge to design a new process more efficient. When we apply this process in the new test campaign, we are able to form these parts in the respect of the requirement from the customers. And according to these customers, compared with the conventional process, we can have a significant cost reduction. The conventional process, we use anneal temper of this material. We use conventional forming operation, 2 die, 2 operation, 1 thermal treatment, and 3 additional operation. And at the end, to respect geometrical tolerance, hammering the manual rework of the plate. The maximum thinning was 15%. In our case, we use directly the good temper of the material, T4. We use 1 die, 1 operation, no thermal treatment, and the maximum thinning at the end is 35%. According to the customer, the cost reduction to produce this part was 40%. Regarding magnetic pulse crimping, in this case, we want to crimp a copper lug on the small wire. It's an electrical connector for aeronautic or automotive application. The wire inside are in copper or aluminum, and the requirements from the customer are to maximize the electrical conductivity of the assembly and to minimize the ovalization of the lug. We use simulation to reproduce existing result, perform in a test campaign, and iterate again to optimize the process. So first, we mesh and we pre-process all the existing setup with a measurement of current applied on the system. It's the first iteration. After, we change the geometry of blue and green part to optimize the ovalization, to reduce the ovalization. And after 5 iterations, we reduce this ovalization by a factor 10 and the maximum temperature in the active zone by a factor 2. It's a good point for the lifetime of this component. When we apply this setting during the test campaign, we are able to remove all the clearance between wires. It's a good point to minimize the resistivity of the assembly, and the ovalization of the lug respects the requirement from the customer. In this example, it's to highlight how we can use simulation to understand the defect and how to fix it during a prototype phase. The product is a panel, aluminum panel, formed with a conventional process, and there is a flanging for the handle. In the flanging, the section in the radius is 2 mm, and we use MPF, a coil. We design a coil to restrict this radius of 2 mm to 1 mm. And during the prototype phase, we have a surface defect, a ghost, all around the profile, 6 mm width. So the challenge of simulation was to reproduce this defect, to understand the origin of this defect, and to fix it. So we iterate with 2D simulation. We investigate on initial condition to track an unexpected initial condition. In this case, the red part is the coil, the green part is the die, and the colored part is the blank. And if we have a bad positioning between the blank and the die, a small gap, it's a yellow circle, we create an impact and we extend the area where we have plastic strain. And it could be the origin of the defect, 6 mm long. When we fix this initial condition, in the workshop, we can change the setting, the localization, the positioning between the blank and the die. We can show in simulation, we have no extension of the area with plastic strain. By this way, we are able to fix this defect without HPP, without change of HPP settings. This part is in production, in the production line today, without defect. The last process, it's magnetic pulse welding. The product here is a high voltage contactor with a silver and copper, a patch in silver on a copper component. It's for electrical network. As usual, we use simulation to optimize, to design the process, MPW process. And there is a requirement from the customer. It's to perform a welding on an area up to 75%. So first of all, we defined the welding window. The welding window, it's impact parameter to, it's a condition of impact to where the welding is possible between the couple of material. It's impact velocity and impact angle. The green zone, it's a good condition to weld. After we perform geometry simulations, and we track this angle and impact on each node on the interface. And we project this couple of parameters on the welding window, and the yellow and green surface on the part indicate where we can expect a welding. We change the settings to maximize this area, the green area. During the test campaign, we are able to weld these two components, and the ultrasound analysis has been performed by the customer, and up to 80% of the surface of the active zone has been welded, and it has been confirmed with a micrography. So it's another example of the good condition defined by simulation and the way while we can use simulation to optimize the MPW process. So regarding simulation service, we propose our expertise in finite element analysis for simple approach or multi-physics approach in mechanics, in thermics, in electromagnetics, aerodynamics, and so on, for static solution to the fast dynamic, for HPP application or not. We perform any studies, feasibility. We can perform component design, conventional forming process, design of the conventional forming process, as usual with simulations. We have special expertise in simulation, in HPP process, and in forming applications. We can offer any trainings regarding HPP and simulation, and we can develop any engineering tools or data processing if required. So study, expertise, trainings, and development. Regarding design of process, HPP or not, we can split in 3 main steps, the simulation activities. The first one can be material identification in static or in dynamic, if the material depends on the strain rate. We can use all these material data for design and optimization of product and process, HPP or not, or conventional forming process, or assembly. And at the end, we can use simulation as a technical support to refit experimental result, to reproduce a defect, and to investigate and to fix it. So in this webinar, we'll present HPP principle, all simulation activities, and we'll highlight the benefits of simulation with very, very simple study cases, and we present the simulation service. In terms of HPP, we want to democratize HPP and to help the customer to integrate specificities of HPP in their product, in their design, in their environment. In HPP or for other applications, we want to propose our expertise in finite element analysis. So the next webinar will focus on each process, HPP process, with more technical detail. So thank you very much for your attention. Now we'll answer to your question. Thank you.
Thank you, Gilles, for your presentation. So we received a lot of questions today. The first one was, how long does a simulation project take?
The time frame depends on the scope of the project. For a simple approach, simple finite element analysis, it could be a few days as usual. For a full design of HPP system to integrate in an existing production line, it could be more important, few weeks or few months. Please contact us to discuss option.
What kind of data do you need to start a simulation project?
Regarding the data, basically we need a CAD file of the part to form or the tolerance regarding the assembly, and a description of the material properties. All the properties can be useful, mechanical properties, electrical properties, thermal properties, and we can characterize material to define the strain hardening in function of strain rate, for example. For forming application, the process description could be very useful to identify where we can implement the HPP operation or to define the initial condition for HPP, MPF or EHF, because the conventional forming fixes the initial conditions. We need a description of the control system and procedure to check if we respect the requirement of the customers. If the part it's an existing part, we can perform any reverse engineering, and we can design a new process, a new forming process from the existing part. It could be less expensive compared with usual forward approach. So, CAD file and material properties.
Does simulation allow to replace the prototyping step?
No, not really. We cannot replace the prototyping step. We can reduce time and cost regarding the prototyping and settings, but simulation must be validated by trials. We are not able to reproduce all the non-perfect conditions of the real world. So we can use simulation to save time and cost, but we cannot totally remove the prototype step.
Okay, thank you. If Bmax process follows a non-Bmax forming process, can you still do simulation?
Yes, of course. We can study conventional forming process in terms of simulation. Sometimes the process, conventional process, define the pre-shape before HPP operation. That's why we developed a specific expertise in conventional forming process to be able to reproduce numerically all the stress and strain in a component before HPP treatment. So we developed a specific expertise in conventional process. Our numerical tools, simulation tools, are very versatile, and we can simulate usual forming process like stamping, hydroforming, and so on, with a good level of confidence.
And can you weld and form in one step?
Weld and form in one step? Not really, no. It's not the same time scale between MPF and MPW. To be able to weld, we we need to respect the specific impact condition. Remember the welding window with impact angle and impact velocity. So a minimum velocity is required to hope to weld. And the high velocity impact between a flyer and a die can be an issue because we can damage the die. So if we consider just the high velocity impact, it's required for MPW process, and it couldn't be an issue. It's usually an issue for MPF application. So no, it's not possible to weld and to form in the same operation, but you can contact us to discuss options about your project.
Another question, can you crimp all diameters?
All diameters. If you want to crimp a very large diameter in MPC process, we have to define a large coil with a large active zone. This large active zone increases the resistance and inductance of the coil, and the generator is not able to generate a high peak of current required to perform the crimping. So for large diameter, maybe we have to develop a new generator, massive generator, to do the job. As you understand, the shape of the coil, mechanical property of the coil defines the electrical property and the electrical response and so on. And so the mechanical loading of the system. So mechanical geometry, electrical property, mechanical loading. It's the coupling. So in Bmax, we are without change, without specific development of generator, we are able to crimp a quite large range of diameter, a few millimeters in diameter and a few hundreds millimeter. It depends on the property of the materials, thickness, and the thickness of the workpiece.
Yes, and by the way, there will be another webinar specifically for this topic, this kind of topic.
Yes, exactly.
So the next question is, are there limitations for forming regarding materials and thicknesses?
For MPF application, a good electrical conductor is better. We can proceed 1 millimeter with a coil, 1 millimeter, 2 millimeter long, and few millimeter width. For electrohydroforming application, the efficiency of the process doesn't depend on the electrical property of the blank, and we can form around 1 meter square. In both cases, it's impact forming, and we can expect an enhancement of formability due to the impact, due to dynamic process, dynamic forming with ironing. And if the material of the blank material depends on the strain rate, we can delay the necking. So we can improve the formability with all the process. Our processes are very relevant for engraving, calibrating, and to reduce the springback defect. Regarding the thickness, for stiffest material, we can form up to 1.6 millimeter thick. And for the soft materials, we can form more than three for very copper, annealed copper, or 2.5 millimeter thick. We work with a large range of materials like copper, aluminum, titanium, and alloys, stainless steel, iron Connell, and so on. So feel free to contact us to discuss about your product, dimension and thickness, and about your materials.
Have you ever characterized the changes of material characteristics due to HPP forming processes?
Yes, of course, yes. We developed specific test beds, as I said before, to define constitutive material law with a strain rate dependency. It's required to be accurate with simulations. We are autonomous to characterize the materials. Regarding the characterization of the final part, we can perform this kind of characterization, but it's always with a partnership with the customers to compare, for example, difference and common point with the conventional forming. So we can perform hardness, measurement of hardness, micrography, grain analysis, but it's always with a partnership with the customer.
And is a press required for HPP processes?
The press is not required. It depends on the project and the process to implement. HPP system can be a standalone system. And in this case, it's very light. It's lighter compared than a press system. But our HPP processes can be integrated in an existing process, like a press. In all the case, technical studies and cost analysis are done to define the best solution, the best processes, compared with conventional process, HPP processes, or hybrid solutions. It depends on needs and the objective of the project.
How is the welding window defined?
So, as said before, the welding window is a set of impact parameters, the condition to respect, mandatory to hope to weld between a couple of materials. So the welding window are defined with impact angle between these two materials and velocity, impact velocity. These limits are defined by the mechanical property and thermodynamics property. So we can define these limits with in theory and numerically to be more accurate. This topic will be presented in detail in another webinar dedicated to MPW applications.
Yes, exactly. How long for a process design?
Cost and time frame depend on the project. The best way is to contact us to discuss options. For instance, forming process design required always any iteration. In Bmax, we iterate with simulation. It's less expensive and it's relevant in terms of return on investment. The future webinar will describe the complex process design by simulation and especially in forming.
Another interesting questions. Are there special requirements to deploy an HPP system into a plant?
Yes, we need electricity, but no, there is no special requirement. We can implement HPP process in all plants in the world. Bmax has installed HPP generator all around the world, in US, in Europe, in India, China, and so on. And all standards can be respected. The requirement must be defined by the customer and will support him for such deployment.
What is the tool lifetime for HPP process?
And tool lifetime for HPP. There is 2 points. The first point is we have to pay attention for forming process, HPP forming process, where we create impact, high velocity impact between two metallic parts, the blank and the die, can create very high stress, and this stress can damage the die. So it's like usual trimming operation. We have to specify the material to use for the die application in function of impact velocity to save the lifetime of the die. Regarding active components for magnetic pulse processes, active components, it's a coil or lifetime where the maximum of current is applied, where the lifetime is defined by electromagnetic loading. Usually for our system, we are able to perform several tens or hundreds of thousands of shoots without change of active components.
One last question. Can we weld all materials with MPW process?
In theory, yes, we can weld all the material, but dissimilar material, steel or aluminum material with aluminum material, silver and copper, dissimilar material, it's possible. And the weldability depends on the strength of material and of both materials, the copper of material. To be efficient, the best is to have a flyer with a good electrical property, a good electrical conductor to maximize the Lorentz force. But if the flyer is not a good electrical conductor, we can weld. We weld, but it could be more expensive and less relevant. But it depends on the application. And we we have success to weld 2 stainless steel parts. So it's doable. And yeah.
Thank you, Gilles, for your presentation and for your time. So we received a lot of questions today. So don't worry if yours were not answered. You will receive a personal answer very soon by email. You can find also the replay on our Bmax channel on YouTube, sorry. You will receive an email with the link in the 24 hours. As we said before, the next webinar will take place in the coming months, so stay tuned on our social medias and websites. And thank you very much for your participation today. We hope to see you again.